Dark matter is one of the most mysterious aspects of the universe. All we know is that a mirror universe exists and only interacts with what we perceive via gravity. We also know that the mirror universe contains the vast majority of the universe's matter. And that's exactly it. One of the most common responses I receive when discussing dark matter is a well-founded doubt and questions about how gravity in the universe may not work on huge scales as we believe it does. All fair game points are strongly represented in the scientific community. The truth is, we don't know what dark matter is. The signs of its presence or evidence are far more extensive than I believe is well acknowledged. The story starts with galaxies. We marvel at all the gorgeous spirals and other structures that should not exist. They should be flying apart, and the observable mass within them is insufficient to generate that much gravity. The physics behind this is fairly simple. If you hurl something about quickly enough, it will desire to fly apart. The galaxies should not be holding together. They are relatively delicate in this sense, but they do. However, this phenomenon is not limited to specific galaxies. The behavior of large-scale structures like galaxy clusters in the universe is also affected by this, as are the motions of individual stars and gas clouds within galaxies. Things that are substantially smaller in scale than they should be if we misunderstood gravity at enormous scales. Gravitational lensing and even the cosmic microwave background provide evidence that dark matter's hand was preserved as a fossil from the very beginning of the cosmos. However, there is another line of evidence. One of the reasons why a substantial portion of the scientific community believes dark matter is an unknown particle in nature is since we already know about one. In a sense, we've already discovered a form of particle that may be classified as or more precisely connected to dark matter. It's the neutrino, and while we can detect them, they're quite difficult to perceive because they're not interactive. They are essentially ghosts. Neutrinos can pass through walls. They can pass through the entire world undamaged and continue on their journey across space. They have mass and interact with gravity, that's all. Aside from that, hitting an atomic nucleus directly inside a detector is purely by chance. Aside from that, they pass through, owing to the fact that these particles are subatomic, meaning they are extremely small, while the atom itself is unbelievably large in comparison to the particles they contain. It's largely empty space inside the atom. So the reasoning is that dark matter may be a particle similar to a neutrino that we don't yet know how to hunt for. Even neutrinos were difficult to find. Early instruments were unable to detect two distinct sorts of them. The problem is that non-interactivity. So the idea that dark matter could be weakly interacting massive particles, or WIMPs, is on the table because we know such particles exist, and we also know that we don't know everything about the types of particles in the universe. So it shouldn't be too strange if there's another out there that we've simply overlooked. However, assumptions must be made, and they are really sound. One of them is that general relativity is correct. This is a huge mess. So general relativity is an incredibly effective theory in that it is testable, makes a variety of predictions, and every time scientists look for proof of those predictions, they discover it. But we also know that some aspects of it are broken because it leads to completely nonsensical answers under certain conditions, such as the singularity of a black hole or below the scale of an atom, where we have a completely different well-proven theory. Quantum mechanics, that is every bit as solid, if not more so, than general relativity, but the two theories do not quite agree. Isaac Newton's science is a fantastic starting point for understanding how this works. His physics was good enough for nearly 2 centuries, properly explaining motion, and it is still used in everything from space exploration to automotive design. It remains the most successful applied physics we have. However, there were some disparities, and Newton himself had unsolved questions. He explains how gravity works, but admits in the Principia Mathematica that he has no idea what gravity is and states, "I feign no hypothesis." We still have that problem, but Newton's contradictions prompted scientists to ask more questions. And they continue to pose questions about Newton. MOND, or modified Newtonian dynamics, is an important question in cosmology that leads directly back to these questions. However, general and special relativity made a significant adjustment that addressed Newton's concerns but also introduced new ones. So it's like a puzzle. The scientists create a description of how things function. Everything happens, and then discrepancies are discovered. The old hypothesis is not abandoned. It is simply revealed to be incomplete. It's similar to a jigsaw puzzle in that you have pieces and can find links, but you also know that you're missing a potentially substantial fraction of the puzzle pieces. You know the picture is incomplete, but you don't know where the missing pieces might be hiding because you're assembling this puzzle on a table with a single dim light overhead. The floor is in darkness, and you haven't yet devised the flashlight you need to see it because not only do you have to build that from scratch using the puzzle pieces as a guide, the picture is of course that of a super collider, but it's a mess, to say the least. But at least you know it's a puzzle that in theory can be solved if you discover all of the pieces and connect them. And perhaps there are some very interesting things lurking in those missing puzzle pieces that will permanently transform physics and open up new paths for how we might apply the new discoveries in our technology. That happened with quantum theory. The equipment you are using to watch this video is powered by quantum effects that Newton had no idea existed, and he lived not that long ago. However, transistors and LEDs both make advantage of quantum phenomena. People sometimes criticize all the money that's spent on quantum mechanics experiments, which are expensive and intense, but the fact is that all internet commerce, content, idea exchange, communication, all the economic growth and advantage of it. The largest companies on Earth today are internet companies and didn't exist before the 1990s when I was already an adult, would not be here without quantum mechanics and the discoveries and developments that came. But all we know about dark matter is the evidence of its effects, not its true form. We have some possibilities, but I believe Newton may have pretended he didn't have any, because while particle nature appears to be the best bet, it could still be incorrect. We may never observe a similar particle, and its nature may either escape us or be discovered in a completely new region, which may happen sooner rather than later. And it may get really odd. A free particle, such as a neutrino that interacts with gravity, is one option. But it's not how our version of the universe prefers to function with its atoms and baryonic matter, predictable gravity, and, well, life. It would be lovely if the solution to dark matter was easy, but it may also be messy, as dark atoms could potentially exist. Dark electrons and dark protons could indicate dark stars producing dark photons, and the dark matter world could be as diverse in physical terms as the baryonic visible world. In a research by Isabella Armstrong and colleagues investigate this hypothesis with dark stars that combine dark hydrogen into dark helium in a completely non-interactive manner other than the gravity they produce. The salvagers and postulate that this could also refer to dark planets and even dark life existing in the same physical space as their apparent counterparts. This was obviously simply theoretical hard science fiction on my side. There is no evidence or indicator of that. But as is often the case, there may have been a seed of something there. The concept of dark stars would be impossible to prove unless the researchers devised a method to verify the notion. Dark stars may be observable if they contain clumps of normal stuff. Dark matter has gravity, so when the mirror stars cruise their galaxy, they may draw a large amount of gas which should heat up and emit observable light. According to the researchers, this may resemble a typical white dwarf with the exception of an exceptionally high X-ray output. This can be searched for. However, there is a potential concern. It has been argued that if dark mirror stars existed, they would have far shorter lifespans than normal stars. However, this requires certain aspects about dark matter and its principles that we do not yet understand. But what's remarkable here is that the concept, with all of its mind-boggling ramifications, can be directly tested by looking for it with hardware that's about to see first light, such as the Vera Rubin Observatory later this year. They will be able to search the telescope's data sets for this signature, which will begin in only 1 year, in 2025. And there is a second potential test there. Dark mirror stars may interfere with regular light flowing through them, creating a very modest characteristic gravitational lens that Vera Rubin may be able to detect. When both of those signs appear in the same item, dark matter is ultimately revealed, bringing up a whole new universe of physics and pretty spooky possibilities. Alright folks, this video ends here. Thanks for watching. Subscribe to my channel for regular, in-depth studies of the fascinating, strange, and unknown parts of our incredible universe.